Welcome to this specialized mathematics lecture on real numbers, designed for Class 10 students. Today, we embark on a journey through the complete number system that structures our physical universe. Think of the real number system as a giant family tree. At the very top, we have real numbers, denoted by the letter R. This vast system splits into two distinct, rival branches: rational numbers, which can be cleanly written as fractions of integers, and irrational numbers, which defy simple fraction forms. As we observe the tree diagram on your screen, trace how rational numbers branch down into integers, fractions, whole numbers, and natural numbers. Each category represents a unique mathematical tool, from the simple count of apples to the complex calculation of infinite orbital shapes. By mastering these connections, you unlock the building blocks of algebra, calculus, and scientific engineering. Let us examine the fundamental theorem of arithmetic, which acts as the atomic theory of number systems. Just as physical matter is made of indestructible chemical atoms, composite numbers in math are made of indestructible prime building blocks. The theorem states that every positive composite integer greater than 1 can be represented uniquely as a product of prime numbers, up to the order of factors. To illustrate this beautifully, look at the factor tree of 120 unfolding on your screen. 120 splits into 2 and 60, which splits into 2 and 30, which splits into 2 and 15, and finally into 3 and 5. The final leaf nodes are all primes, yielding a unique factorization: 2 raised to the power of 3, multiplied by 3, multiplied by 5. No other prime combination on Earth can build 120. The fundamental theorem of arithmetic is not just dry theory. It drives real-world engineering. Let us explore HCF, the highest common factor, and LCM, the lowest common multiple. Imagine two interlocking mechanical gears on a machine. Gear A has 12 teeth and gear B has 15 teeth. They start spinning, and we want to know when their starting notches will align perfectly again. This question is solved by finding the lowest common multiple of 12 and 15, which is 60 teeth alignments. By prime factoring both numbers, HCF is found by taking the product of the lowest power of common primes, which is 3. LCM is found by taking the highest power of all active primes, yielding 60. Interlocking gear mechanisms rely completely on this arithmetic alignment ratio to ensure mechanical precision. For centuries, mathematicians believed that all numbers could be written as clean, orderly ratios of integers. This belief was shattered when ancient thinkers discovered lengths that could not be measured by fractions, the irrational numbers. On the infinite number line displayed before you, notice how integers and rational fractions sit neatly at regular spots. Yet, packed between these rational points are infinite gaps, or slots where irrational numbers rest, such as the square root of 2 and the value of pi. If we zoom in using our visual magnifying glass between 1.4 and 1.5, we see exactly where the square root of 2 lies: 1.414213, continuing infinitely, without ever ending and without ever repeating. They represent infinite mathematical chaos nestled within perfect geometric order. To prove that a number like the square root of 2 is irrational, mathematicians use a powerful detective method called proof by contradiction. Instead of proving it directly, we assume the opposite, that the square root of 2 is rational. We write it as a fraction a over b, where a and b are integers with no common factors, meaning they are coprime. By squaring both sides, we get 2 equals a squared over b squared, which simplifies to a squared equals 2 times b squared. This means a squared must be an even number, so the integer a must be even. If a is even, we can write it as 2 times c. Substituting this back gives 4c squared equals 2b squared, which simplifies to b squared equals 2c squared. This means b is also even. Contradiction: if both a and b are even, they share a factor of 2, violating our assumption that they are coprime. We can construct the square root of 2 geometrically using a simple right-angled triangle. As shown in the geometric coordinate construct on your left, we draw a right-angled triangle with a base of 1 unit and a height of 1 unit. By applying the Pythagorean theorem, the hypotenuse squared is equal to the base squared plus the height squared, which is 1 plus 1, or 2. Therefore, the hypotenuse has an exact length of the square root of 2. To visualize where this length rests on our physical number line, we sweep a circular arc originating from 0 down to the number line. The arc crosses the scale exactly at 1.414. This geometric construction proves that although the square root of 2 cannot be written as a clean numerical fraction, it exists as a perfect, exact physical length in space. To deepen our algebraic understanding of real numbers, we must extend our knowledge of powers and exponents to fractional domains. We know that 2 raised to the power of 2 is a simple grid multiplication resulting in 4. But what does 2 raised to the power of 1/2 actually mean? A fractional exponent represents a radical power. 2 raised to the power of 1/2 is simply the square root of 2. In the visual panels on your left, observe the comparison. An integer power is illustrated as a grid expansion, while a radical power is shown as a side length that yields a targeted square area. For instance, a square with an area of exactly 2 units squared has side lengths of 2 raised to the power of 1/2. By mastering these radical laws, we solve complex algebraic equations in physics and chemistry. The rigorous proof by contradiction method we used for the square root of 2 applies universally to other prime radicals, such as the square root of 3 and the square root of 5. As shown in the logic flow panel, we begin by assuming the square root of 5 equals a over b is a rational fraction where a and b are coprime. Squaring both sides yields 5 equals a squared over b squared, which leads to a squared equals 5 times b squared. This dictates that a squared is divisible by 5, which means the integer a must be a multiple of 5. We substitute a equals 5 times c, yielding 25c squared equals 5b squared, which simplifies to b squared equals 5c squared. This dictates that b is also a multiple of 5. Both integers share a common factor of 5, destroying our coprime assumption and proving irrationality. What happens when we combine rational numbers and irrational numbers together? We get algebraic combinations, like 3 plus 2 times the square root of 5. Proving the irrationality of these combinations is remarkably simple and elegant. We assume the entire combination is rational, setting 3 plus 2 times the square root of 5 equal to a rational number r. By rearranging the terms to isolate the radical, we get 2 times the square root of 5 equals r minus 3, which simplifies to the square root of 5 equals r minus 3, all divided by 2. Since r, 3, and 2 are rational, the entire right side must be rational. But this means the square root of 5 is rational, which is a contradiction. Since this is impossible, the initial sum 3 plus 2 times the square root of 5 must be irrational. Finally, we examine the decimal expansions of real numbers, which provide a beautiful visual summary of our entire number system. Rational numbers exhibit highly ordered decimal expansions. They either terminate, like 3/8, which equals 0.375, or they repeat infinitely in cycles, like 1/3, which equals 0.3333 repeating. The fundamental theorem of arithmetic dictates that a fraction will terminate if and only if the prime factorization of its denominator contains only factors of 2 and 5. In contrast, irrational numbers like the square root of 2 and pi have non-terminating, non-repeating decimal expansions that continue forever in infinite, beautiful chaos. By understanding these decimal laws, we connect pure algebra to the computer screens and processors that power modern digital technology.